Learners of mathematics, welcome to section 2 of unit 6. That's groups. So in the previous session, we look at what an algebraic structure is. In this session, you will learn about groups, which are the most basic and most important structure on a set. You will learn how to define group. Also, you also learn to give some examples and state some of its common properties of groups. I am Nkaila Dasmani, your course instructor for this course. By the end of this session, you should be able to define a group, give at least 3 examples of a group, give at least 1 example of a non-group, and state and prove at least 2 basic properties of a group. Definition of groups. We have 2 definitions we are going to look. First, we look at definition 1. Let G be an empty set with a binary operation star defined on it. Then the pair G star is called a group if the following 3 axioms are satisfied. Okay, I didn't give the axioms here. Let me give them to you. So the first axiom, let's say G1, we have the star should be associative. So if you have A, B, and C being a member of G, we are saying it's associative. So one can say that A operation, B operation, C is actually equals to A operation, B operation, C. Okay, then we say that operation is associative. Let's cut 2. There exists this E being a member of G. I know you know where the E comes from. The E is what we refer to as identity element, such that A operation E is actually equals to E operation A, and that must be equals to A. Don't forget about your right and left identity element. So once the right and left identity elements are equivalent, and the answer is A for that group. So that's the second axiom. So the third axiom is that for each A in G, there's another also element in G. We refer to as A inverse also in G, such that A operation, its inverse, is actually the same as A inverse operation A, and the answer is what? Answer is E. Okay, in that instance, we refer A inverse as the identity element. So when these 3 axioms are satisfied, then we say that the operation is a group. The operation is a group. So that defines the group. The most basic and most important structure on this set, as I've mentioned earlier, is a group. So in this set of elements with an operation that satisfies these 3 axioms, we refer that set as a group. Great. Example. Let's see example. The set of integers forms a group under the operation of addition. The set of integers form a group under the operation of addition. So you know operation of addition, A plus its inverse equals to the identity element. You remember that. And what is the identity element of addition? You can see the identity element of addition. Let me clean this one. So when I have A plus 0 is same as 0 plus A, which equals A. Therefore, E is actually equal to 0. So once you're able to establish that the identity element is 0, then we can also have, that it's automatically, associative. When you pick 3 numbers, 2, 3, 4 is actually associative. And likewise, you can also find an inverse element, A inverse. So once you find inverse element, that is negative A, actually, that 3 conditions satisfied, then we say that the set of integers forms a group. The second one is the set of real numbers. It also forms a group under the addition. The set of real numbers form a group under addition. Explain. Just go ahead and prove as I've done. Then the set scale of rational numbers forms a group under addition, and then a set of complex numbers. We just look at the complex numbers, don't forget about the square root of negative numbers, forms a group under addition. So it's very beautiful. Go ahead and then you can also explain this thing, prove them. Let's look at this definition 2, definition of group, definition 2. So a group that is G of star is called abelian or commutative if the binary operation G is commutative or commutativity hold. So that is self-explanatory. So when we have A operation B equals B operation A, for all A, B being a member of G, then we say that the operation star is an abelian group or is commutativity. That's commutativity hold. So it's an abelian group. Okay. Let's look at this example 2. Example 2. So the set R of real numbers forms an abelian group under addition, and I'm sure you agree to that. Similarly, the complex numbers forms an abelian group under the addition. You can try burst and then go ahead and do more, prove more. Let's look at elementary properties of groups. Elementary properties of groups. We now turn our attention to discuss some of these elementary properties. I'll try to prove some for you, which some will be leaving for you to go and prove. But this, I'll make sure I prove the difficulty aspects. Okay. The identity element for group is unique. That's the first one. This is just, it's just basic. So identity element for group is actually unique. I'm sure you can prove this one. And then the second one, each element in the group has a unique inverse. A unique inverse. So simple. And we have already gone through this. So I leave to you as a proof. So, elementary property 3. The inverse of an element is the element itself. And this is very simple and self-explanatory. It looks like very interesting. The inverse of an element is the element itself. As in this one, let me try to help you to prove. So, if you let A to be a member of this G, what it states is that the inverse, let me clean this and then space more. The inverse of the inverse, that is the inverse of an element is the element itself. So something like this. So let's prove. Now we know that from the previous session that when I have A inverse times A, what do I get when I multiply any inverse by that number? What do I get? So remember, I get identity elements. I hope you remember that. You remember that. Okay. A inverse times A is equals to the identity element. Once you've understood that, now let's see. Let's try to do some important thing here. When we pre-multiply this by A inverse, what do we get when we pre-multiply this by A inverse? So from here you get, let me call this equation 1. So let's pre-multiply the expression. The expression is here. A inverse or inverse equals to A. So I'm going to pre-multiply, let me call this equation 2. Okay. So when we pre-multiply this equation 2 by A inverse, I'll get A inverse times A inverse or inverse, and this equals to A inverse times A. And I think you agree with me. So what do I get? You can see that, so here A inverse times A inverse, we multiply the A inverse by its inverse like this. Okay, so that is A inverse times its inverse. What do I get? This is look like very interesting. A inverse times A, that's from equation 1. You see, gets the identity element. Now we have the inverse multiplying by the inverse times its inverse, and it looks like equation 1. So what do you get? And that becomes A inverse. That's A inverse or inverse is actually equal to A. That's from equation 1. We can deduce that. And when this one is established, it means that it proves for the axiom that the inverse of an element is the element itself. You see, the proof is very simple, but you can also use different alternative proof, but this looks so simple. Okay, so axiom 4, unfortunately I didn't state it here, but let me state it for you. If you have A, B, be a member of the group G, so let me write it. A, B, be a member of the group G, then there's an important deduction one can make from here. So the axiom states that when you have the product of A and B or inverse, and then the result is B inverse, A inverse. Very, very interesting. So the product of A or inverse is actually equals to the B inverse times A inverse. I remember some quite time ago, WAEC elective math, they give some question like this for students to prove, but they didn't tell them that this is a property, but they employed that property over there. So this axiom is very, very, very interesting. Okay, so how do we then prove for this axiom 4? The proof is so simple, so simple. So now let's suppose A, B are members of G. Then what can we say? If I have, we know that inverse times its element is equal to, what do we get? The identity element. I think we agree to that. So we are going to prove to see if we get the inverse times its element to get the identity element. So from here I can say that A B multiplied by the product of AB, or let's say B inverse A inverse. Let me start from that. B inverse A inverse. What do I get? This one will be actually equal to, you see, this one you get A here, and then I can, it's multiplication, so it's commutative. Then I can say B inverse. I think you agree with me, times A inverse, and that's actually true. And B times B inverse, what do I get? B times B inverse is the identity element, so A inverse. And I think when you multiply identity element by any number, it doesn't change. The meaning remains the same. It's like if you have your father and then you tell your secret to your father actually will keep it, so it doesn't change anything. Okay, so you get A times A inverse, and what will be the result? A times A inverse will give you the identity element. So once this condition is satisfied, we can see therefore AB or inverse equals to B inverse A inverse, and that proves, or that proof for this axiom. Very, very interesting. So go through and then prove more. So let's look at property 5, or the axiom 5. If A, B, and C are elements of a group G, then the cancellation laws hold. So you have two cancellation laws, right cancellation and then the left cancellations. So let me help you to prove these two laws, because they are very, very interesting. Okay, so as you've already said that you know that let A, B, and C be a member of G. Then once A, B, and C are members of G, then for the cancellation law, so the first one, let me look at right cancellation. So once the cancellation law hold, right cancellation law. So what it states is that B star A equals to C star A. If B star A equals to C star A, it implies that B equals to C. Okay. Once B star A equals to C star A, it implies that B equals C, and this is actually true. If 3 times 5 equals to 7 times 5, then you can actually say that 3 equals to 5. And that looks somehow, when you use numbers it doesn't sound good, but when you use letters or variables it looks like very true, but when you use numbers it sounds some way. But let's see how the proof is. How the proof is. So assuming, okay, let me underline this that the proof starts. We know that B star A is actually equals to C star A. Then we can say that we are proving from that, so we can say that B equals to, you know that B is the same as B operation, the identity element. So B operation, its identity element, and the same as, let me say B operation, if I write A inverse or A operation, its inverse, I think they are the same, right? They are all equivalent, right? So once these are true, let me put this in brackets, then you can say that this is the same as B operation A. So by using the commutativity, so I can get B operation A and then operation A inverse, and I hope you agree with me. B operation A inverse. So you get something like that. And it's the same as, don't forget about B operation A is the same as C operation A. So I can write C operation A here. Operation A inverse. Okay. I think you agree with me. And it's the same as, I can write this as C operation commutativity law A operation A inverse, and I'm sure you agree with me. And that's, and A operation its inverse is the same as the identity element. So I get C operation its identity element, and that is, so we are having B operation its identity element same as B, and you agree with me. So C operation its identity element is same as C. So in that instance, we say that this proves the right cancellation law. So by the right cancellation law, this proves, and it's very interesting. Okay, so let's see the left cancellation law. So the left cancellation law, let's see this one. The same is your definition when we're having A, B, C, which were members of G, and we're saying that when you have A star B equals to A star C, that this implies that B equals to C, and that is what you call the right cancellation, left cancellation. You can see there on the left side, so left cancellation. Okay, left cancellation law. So the proofs, I don't know whether I should leave to you for as an assignment. Okay, let me help you out. Okay, so the length of the video will be very long, so go through the first one. We did the same step, and then at the end of the day you arrive at the same conclusion following the same step as the previous one in order to shorten the video. Okay, it's very simple and very interesting. So in this session we look at what group is, and also look at elementary properties of groups. Read more in your course materials.